Hi friends, today I am giving a lecture on identifying the articulation points in a given graph. Articulation point is a vertex. By deleting that vertex and incident all the edges on that vertex, because of removing that vertex and all its incident edges, then that graph is divided into two or more non-empty components. Then that vertex is called as articulation point. Okay. Now, how to identify the articulation points in a given graph, we have to discuss in this video. If the graph consists of n greater than or equal to vertices, then we have to find that how many number of articulation points are exist in a given graph. This is the problem statement. So this is the given graph. For this graph, how many number of articulation points are available? So that can be determined by using depth first spanning tree for the given graph. Okay, first we have to draw the depth first spanning tree for the given graph. Okay, the depth first spanning tree for the given graph is shown in figure 2. Okay, here there is a number outside of each vertex in depth first spanning tree for the given graph is shown in this figure. Okay, this number is called as depth first number. Depth first number indicates the order in which DFS visits the vertices in the given graph. That means in which order the DFS visits all the vertices of the given graph G. So that number is called as depth first number, that can be represented by DFN. Okay, now consider this graph, how we are visiting the vertices by using depth first search. First, we are starting at vertex 1. Okay, then the depth first number is equal to 1 because we have to visit the first vertex in DFS order. Now, vertex 1 DFN number is 1. Now, we have to visit next vertex is 4. Okay. So first we have started the DFS search at vertex 1. Okay, the first vertex to be visited is vertex 1. Then DFN number is equal to 1. Next visit the vertex 4. Okay, after visiting vertex 4, what is the DFN number? That is second vertex in the DFS order. So the DFN number of vertex 4 is 2. Next, visit the vertex 3. Okay, DFN number of vertex 3 is 3. Next, visit the vertex 10. DFN number of 10 is 4. Here there are no childs for vertex 10. Again, we have to backtrack. Go to vertex 3. Next, go to this side. Now visit the vertex 9. So, next, there are no childs for vertex 9. Again, we have to backtrack to vertex 3. Next, go to vertex 2. Next, go to vertex 5. Next, go to vertex 6. Here there are no childs for vertex 6. Again we have to backtrack to vertex 5. Next go to vertex 7. Next go to vertex 8. Now we are already visiting all the vertices of the given graph exactly once. Okay. So now what is the order we have to follow the DFS to construct the DFS spanning tree? 1, 4, 3, 10, 9, 2, 5, 6, 7, 8. Now DFSN number. DFN number of vertex 1 is 1. DFN number of vertex 4 is 2. DFN number of vertex 3 is 3. DFN number of vertex 10 is 4. DFN number of vertex 9 is 5. DFN number of vertex 2 is 6. DFN number of vertex 5 is 7. DFN number of vertex 6 is 8. DFN number of vertex 7 is 9. DFN number of vertex 8 is 10. Okay, so this is 1, 4, 3, 10, 9, 2, 5, 6, 7, 8. DFN number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is the depth first spanning tree for the given graph is shown in figure 2. Okay, now DFN number of 1 is 1, DFN number of 4 is 2, DFN number of 3 is 3, DFN number of 10 is 4, DFN number of 9 is 5, DFN number of 2 is 6, DFN number of 5 is 7, DFN number of 6 is 8, DFN number of 7 is 9, DFN number of 8 is 10. Okay, this is the vertex number. This is the number outside of each vertex that indicates the order in which DFS visits all the vertices in the given graph. That can be named as depth first number, that is DFN. So here this is vertex 1, this is DFN number. This is vertex 1, vertex 4, this is DFN number. Vertex 3, DFN number. Vertex 10, DFN number. Vertex 9, DFN number. Vertex 2, DFN number 6. Vertex 5, DFN number of 7. Vertex 6, DFN number is 8. Vertex 7, DFN number is 9. Vertex 8, DFN number 10. Now this is the DFS spanning tree. This DFS spanning tree is used for identifying the articulation points in the given graph. Now this is the depth first spanning tree. What are the edges present in the depth first spanning tree are called as tree edges. So tree edges represents the solid lines. So this is solid line, this is solid line, this is solid lines. Okay, what are the edges present in the depth first spanning tree are called as tree edges. These tree edges are represented by using solid lines. Next, dotted lines of depth first spanning tree are called as back edges. So back edges are nothing but the remaining edges present in the given graph except the edges in depth first spanning tree. Okay, what are the edges that are present in the depth first spanning tree? Then the remaining edges of the given graph G are called as back edges. So back edges are represented by using dotted lines. Okay, so the collection of tree edges and back edges is nothing but the number of edges present in the given graph G. Okay, tree edges are nothing but edges present in the depth first spanning tree. Whatever the remaining edges are there, that remaining edges are called as back edges. That back edges are represented by using dotted lines. Tree edges are represented by using solid lines. Okay. Next one is, suppose if u comma v is an edge of a depth first spanning tree, then u is ancestor of v or v is ancestor of u. So both are correct. So if u comma v is an tree edge of depth first spanning tree, then either u is ancestor of v or v is ancestor of u. Okay, for v, u is ancestor, for u, v is ancestor. Both are correct. Next, the root node of a depth first spanning tree has two childs, then the root node is called as an articulation point. So the root node of a depth first spanning tree is called an articulation point if and only if it has two children. For example, node 1, vertex 1 is called as an articulation point if and only if this is the root node of the depth first spanning tree and it contains two childs. Okay, if and this root node of a depth first spanning tree, that is vertex 1, is called as an articulation point if and only if it has two children. For example, this is the root node of a depth first spanning tree. This node 1 is called as an articulation point if and only if it has two childs, but it has only one child, that is vertex 4. It is the back edge, not the tree edge. So it has only one child. Then we can say that the root node of the depth first spanning tree, vertex 1, is not an articulation point. Okay, we can say that the root node of the depth first spanning tree is called an articulation point if and only if it has two childs. Next, suppose if u is any vertex other than root in depth first spanning tree. Okay, the vertex u is not an articulation point if and only if the child of u, that is w, and its descendants makes a path to reach the ancestor of u, then we can say that u is not an articulation point. Now, for each vertex u, L of u is the lowest depth first number reached from u using a path of descendants followed by at most one back edge. Okay, what is the meaning of this one? L of u is any vertex other than root. L of u is the lowest depth first number, lowest DFN number that can be reached from W. We have to reach the vertex. U using a path of descendants of followed by at most one back edge. Okay. So L of u is calculated by using this formula, minimum of dfn of u, whatever the vertex you can take. First we have to find out the dfn value. Minimum of dfn of u, lowest depth first number that can be reached from u. That is nothing but depth first number. Minimum is nothing but lowest. Lowest depth first number that can be reached from u using a path of descendants. Using a path of descendants. Here L of w by w is a child of u. That is nothing but w is the descendant of u. And at most one back edge. Minimum of dfn of w, u by w is a back edge. Okay, this is the total description of L of u is nothing but L of u is equal to minimum of lowest depth first number that can be reached from u using a path of descendants of u with followed by at most one back edge. Okay, at most one back edge. Okay, so we have to find out the minimum of this one and this one. So for example, we can go to L of 10. Here u is equal to 10. L of 10 is equal to minimum of dfn of 10. So here whatever the number outside the vertex, that number represents the depth first number. Here depth first spanning tree is drawn. So in this way, so the number outside of each vertex is nothing but depth first number. So we have to visit the depth first spanning tree in postfix form. Okay. So according to the postfix form, we have to visit first 10, next 9, next 6, next 8, next 7, next 5, next 2, next 3, next 4, next 1. So 10, 9, 6, 8, 7, 5, 2, 3, 4, 1. Okay. Now we have to calculate the L values according to the postfix form of the following depth first spanning tree. Now L of 10 is equal to minimum of dfn of u. U value is 10. Dfn of 10, comma, minimum of L of w. So here for the node 10 there is no descendants. So no descendant, there is no back edge from 10. So is equal to minimum of dfn of 10. Dfn of 10 is nothing but 4. So there is no descendant for node 10. So nil. There is no back edge from 10. Nil. So minimum of 4 comma nil comma nil is equal to 4. Next, L of 9. L of 9 is equal to minimum of dfn of 9. So dfn of 9 is nothing but 5. So 5, there are no descendants, there is no back edge. So that is 5 nil comma nil. So that is nothing but 5. Next, L of 6. Next visit the vertex is 6 according to the postfix form 6. So dfn of 6. Dfn of 6 is 8. Minimum of dfn of 6 is 8, comma, there are no descendants, there is no back edge. So that is 8 comma nil comma nil. Minimum of 8 comma nil comma nil is equal to 8. Next one is L of 8. L of 8 is equal to minimum of dfn of 8. Dfn of 8 is 10, comma, there are no descendants. So that is nil. There is a back edge from 8 to 2. So here this is W and this is U. So that is DFN of W. DFN of 2. DFN of 2 is 6. Okay. So L of 8. First L of 8 is equal to minimum of DFN of U. DFN of U is nothing but DFN of 8. That is 10. There are no descendants for vertex 8. That is nil. But there is a back edge is there. There is a U comma W is a back edge. Here U is equal to 8. W is equal to 2. 8 to 2. So then DFN of W. DFN of 2 is nothing but 6. So that is 10 comma nil comma 6. That is equal to 6. Next, L of 7. L of 7 after 8 according to the 4 sticks. Next visit the vertex 7. L of 7 is equal to minimum of DFN of 7. DFN of 7 is 9 comma. Next, what are the descendants for node 7? Only 8. Okay. So here L of 8. L of 8 already we have calculated. That is 6 comma. There is a back edge is there. 7 to 2 back edge is there. So here this is U and this is W. So that is DFN of 2 is 6. So 9 comma 6 comma 6. The value is equal to 6. Next, after 7, next we are visiting the vertex 5. So L of 5 is equal to minimum of DFN of 5. DFN of 5 is 7. Next, what are the descendants? So that is 6, 7 and 6 and 7. Among them, which is the lowest L of 6? L of 6, what is the value? 8. L of 7. L of 7, what is the value? 6. Among them, which is minimum? That is 6. So that is 6. There is no back edge. From 5 to there is no back edge. That is nil. So 7, minimum of 7 comma 6. That is 6. Next, L of 2. After 5, next go to vertex 2. So L of 2 is equal to minimum of DFN of 2. DFN of 2 is 6 comma. Next, what are the descendants for 2? So here 5 is there. So L of 5. L of 5 is 6 comma. There is a back edge is there. That is 2, 1. Here U value is 2. W value is 1. So L of 1. L of 1 value is equal to 1. So 6 comma 6 comma 1. That is equal to 1. Next go for L of 3. L of 3, this one, minimum of DFN of 3. So that is 3 comma. What are the descendants are there for 3? So 10, 9, 2. Among them L of 10. L of 10 value is 4. L of 9. L of 9 value is 5. Next L of 2. L of 2 value is 1. Among them which is minimum? 1 is the minimum. There is no back edge is there. So minimum of 3 comma 1 is nothing but 1. Next go for L of 4. So L of 4, minimum of DFN of 4. DFN of 4 is 2 comma. What are the descendants for 4? Only 3. So what is the L of 3? L of 3 value is 1 comma. There is no back edge is there, nil. So minimum of 2 comma 1 is equal to 1. Next L of 1. L of 1 is equal to minimum of DFN of 1. DFN of 1 is 1 comma. What are the descendants are there? Only 4. So what is the L of 4? L of 4 value is 1. There is no back edge, nil. So then the value is equal to 1. So now L of 1 to 10 is equal to L of 1 to 10 is equal to L of 1 value is 1. L of 2. L of 2 value is 1. L of 3 value is 1. L of 4 value is 1. L of 5 value is 6. L of 6 value is 8. L of 7 value is 6. L of 8 value is 6, L of 9 value is 5, L of 10 value is 4. Okay. Now, suppose U is an articulation point. So then U is not the root if and only if U has a child W such that L of W greater than or equal to DFN of U. So this is by using this condition. So we have to calculate whether the vertex is articulation point or not. Okay. So for that purpose we have to find out the L value and DFN value. Okay, suppose vertex 2 has a child 5. So vertex 2 has a child 5. So U is equal to 2, W is equal to 5. Next, L of W, that is L of 5 greater than or equal to DFN of U. U value is 2. L of 5. L of 5 value is nothing but 6 greater than or equal to DFN of 2 is 6. 6 greater than or equal to 6, that is true. Now we can say that 2 is an articulation point. Next, vertex 3 has a child 10. Vertex 3 has a child 10. Now U is equal to 3, W is equal to 10. L of 10 greater than or equal to DFN of 3. L of 10 value is 4, DFN of 3 is 3. 4 greater than or equal to 3, true. Now we can say that 3 is an articulation point. Next, vertex 5 has a child 6. Okay, here U is equal to 5, W is equal to 6. L of 6, L of W is L of 6 greater than or equal to DFN of U, DFN of 5. L of 6 value is 8, DFN of 5 value is 7. 8 greater than or equal to 7, that is true. Now 5 is an articulation point. So for the given graph, the articulation points are 2, 3, 5. Okay. So thank you for watching this video. If you like this video, please subscribe my channel name Divvela Srinivasa. Divvela Srinivasa. Thank you. So by using this procedure, we have to find out the articulation point by calculating the L value and DFN value for each and every vertex in the depth first spanning tree. So thank you.